Hi, so today we will talk about one of the most important part in chapter 7, which is 7.8, improper integral. So this part of the chapter will contain much likely one of the most important part and for the exam too. So I guess uh, so today I will talk about I will give the brief definition and three examples of three types of the improper integral. So you have type one of integral. Okay, much better. So for type one of the improper integral is that when you have one of the bound is infinity. So if you have an equation from a to infinity of fx dx, what you're gonna do is you're gonna make it equal to, and you make sure that a d is like larger than a, so it will be equal to the limit of t to the infinity of the integration of a to t fx dx. Or if it is going from minus infinity, obviously you cannot go from infinity to something. So it has to be from minus infinity to, let's say, b of fx dx. It will be equal to the limit from t to the minus infinity of from d to b of fx dx. Okay, so that's the part. Okay, so when you calculating the limit, there might be a chance that the limit does not exist, and there might be a chance that the limit did exist. So if the limit exists, we call it conversion. We call that the integral is conversion. And if the limit So if the limit does not exist, it will be called divergent. So it will be called divergent. And that's one type of the type 1 of improper integral. So, and you have one very small definition, like theorem. But it is very important that if you have an integral goes like this from 1 to infinity, and of 1 over x to the power of p dx. So if you have p less than 1, if your p is less than 1 or equal to 1, the integral will be divergent. And if p larger than 1, it will be convergent. And so that's the type 1 of the improper integration. So let's take a look at an example. And let's take a look at an example about the type 1 of the improper integral. So determine the integration from 2 to infinity dv over v squared plus 1v minus 2. So as you see that this is type 1 of integration, and what we are going to do is we're going to make this infinity equal to one variable t. So it will be equal to the limit of t to infinity of dv over v squared 1v minus 2, and it will go from 2 to t. All right. Okay, so this is the type that you met on 7.4. So how are you going to solve this problem? How are you going to solve this integration? So when you look at this one, it will be, you surely have to use partial fraction for this problem. So you will still calculating. So how you're gonna do this problem is you're gonna still calculating this one first, this equation first, and then when you see, then you will calculate the limit. So this one surely is partial fraction, which means it will be equal to the limit of t to infinity to of dv over v plus 2 times v minus 1. Okay, so after doing the partial fraction, which you just have in 7.4, it will be equal to the limit t to infinity of 2 to t. The I will be minus 1 over 3 over v plus 2 plus 1 over 3 of v minus 1 dv. That is a much better solution now. So after calculating this one, the integration part, you will get, because now you can like moving the 1 over 3 outside, and then just calculating 1 over v plus 2 and 1 over v minus 1. And after that, it will be equal to minus 1 over 3 log pair of v plus 2 plus 1 over 3 log pair of v minus 1 from 2 to t. And don't forget the limit over here. Okay? Which is, in fact, you have you actually have LV ln of like A minus ln of B will be equal to ln of A over B, right? So when you apply to this one and you let the 1 over 3 like outside of the bracket, it will be like just like that, and it will be the limit when t to the infinity of 1 over 3 v minus 1 over v minus 2, v plus 2, sorry, from 2 to t. which will be equal to the limit t to infinity of ln t minus 1 over t minus 2, t plus 2, sorry, minus ln of 1 over 4. So when t goes to infinity over t, so you have the limit when t goes to infinity of this one is one indeterminate form, like infinity over infinity, right? So what you're gonna do is you're gonna apply the L-Hospital rule, right? Apply the L-Hospital rule, will leave. Oh, sorry, not that. Oh yeah, yeah, yeah. So it's still the infinity over infinity. So you're gonna use the L-Hospital rule for this part right here, and it will be 1 over 1, which will be 1. And then the ln of 1 is 0, right? So you have this limit right here go to 0. And so which will lead to, it will be equal to, sorry, to, oh, I forgot the 1 over 3 over here, sorry. It will be equal to over 3 of minus ln 1 over 4. This one is surely conversion because it's not equal to 0, it's not equal to infinity. Like it did not go to infinity. So if the limit goes to infinity, it will be diversion. So this one is conversion. Now that's one example of the first type. Let's move on to the second type. The second type state that, oh, I forgot. So let's take a look at an example in the minor theorem. And this one is very important because I remember that in the exam there will be like one problem about this part. So if you have like 1 to infinity of 1 over x3, it will be converged. And if it is 1 over to infinity of 1 like x to the power of 1 over 2, 1 over x to the power of 1 over 2, it will be diverged. dx, dx. It will be diverged. Remember this theorem. It is very important. Okay. How about the second part? So if the function fx is discontinuous, and A or B, like if you have the range of fx go from like A to B or A to B, which means the function is like discontinuous at A or discontinuous at B. What you're gonna do is you're gonna change it like just the way with the infinity, but rather with A. You change B with T or A with B with T. Like it treat the discontinuous point like infinity, and the limit will go from the limit from T to B minus, or the limit T to A plus, limit to B minus only when B is discontinuous, and if A is discontinuous, like change it to the limit of T go to A plus. So that's all for today. I will talk about the rest of the actually there's still time, so I'll talk more about this one. And for if you have like a range where like A less than C less than B, and you have the integration of 1A to C of fx dx, and from C to B of fx dx converge. So the integration of A to B of fx dx equal to A to C of fx dx plus C to B of fx dx. That is when the function is discontinuous at C. So you have to break down into two parts and make sure that the two parts that you're breaking down are converged. If not, there's no point to like change it to the sum because it diverges anyway. And last but not least, is the comparison theorem. So you can look up the text in the textbook about the theorem, but let's visualize it by the graph. So you have two functions, fx and gx. And let's assume that fx is larger than gx. Let's assume that fx is larger than gx. So when you draw the graph like this, let's take an example where gx is converged, is diverged. So when gx is diverged, it will go like this one, but it never touched the ox. And then let's have gx. So this one will be gx. And let's make it colorful. Okay, so you have here is the graph like coordinate. Now you have here is gx, and at this example we'll assume that gx is diverged, which means it would never touch the ox. So this is gx. And because fx is larger, it is larger than gx, so fx will be like this one. But because gx is diverged, so fx can never intersect with gx, which leads to the fact that fx is also diverged because it cannot pass gx. So gx must also be diverged. So this is part one of the theorem. Where if gx is diverged, fx also will be diverged. Let's take a look at another graph. And gx is still smaller than fx. So this is fx. And let's assume in this example, fx is converged. Yeah, it will converge because it passed this point of the line. Gx is smaller than fx, so it will have to be like this one. And it is gx. It is because fx is converged, and gx is smaller than fx. So when you draw the graph of gx, it cannot be diverged because it will intersect with fx like at a certain point. So yeah, so this is the second part of the theorem. That means if you have, if you have fx is diverged, is converged, gx will also be converged. This one is a very important theorem because they will come at a problem where it is impossible to solve the integration or the limit of that problem. And when you change it to a much easier problem, like if you have like 1 over x squared plus 3, it will be like larger than 1 over x squared, right? And you surely know that 1 over x squared is converged, which will lead to 1 over x squared plus 3 is also converged. So that will be much easier than to like calculating the limits and do all those stuff, because you cannot apply the p squared theorem on this equation, but you can do it over here. So that's the overview of 7.8. I will talk like much more about this on this Thursday, because it is such an important section in the book. So I will talk about it on Thursday. Thank you guys for watching.